Our original thrust was in the textile industry, paper mill industry, and that kind of a thing. But when diesel power came along, we got into the railroad liner business and have been the leader in that, in the locomotive industry since the very beginnings of diesel power. We are the only supplier to major OEMs for chrome plating on new power cylinders. We supply all of EMD's requirements, General Motors requirements, General Electric, and Fairbanks Morris, and Alco when they were in business, and that's been taken over since by Fairbanks. GE still has a piece of that actually, but we supply all of the OEMs with chrome plating on new power cylinders as well. In the large engine field, and at one time we were the source of supply for Ball and Hamilton until they went out of business. And we do a lot of remanufacturing or reclamation on some of those parts across, but unfortunately those are rapidly dying. But in the large engine, about 1985, our process was approved by Cooper, and we are now the only source of supply to Cooper for hard chrome on new power cylinders there. And we do the vast majority of the aftermarket or rebuild work on Cooper liners as well. Clark and Ingersoll generally do not have chrome on their new parts, new cylinders, new power cylinders, but they do use, depending upon the individual locations, they will use chrome to reclaim them. The Worthington is the only now Clark cylinder that uses chrome on new, but there just aren't that many of those around anymore either. So we're seeing a lot of changes in the marketplace with that regard, but we continue to supply Cooper with all of their requirements on new parts. Our company, they said, has been around for a long time. We've always been tied in with the OEMs. Consequently, we aren't very well known out in the field, particularly in the large engine. Most of the railroad people know of this, but in the large engines, pipeline, gas transmission, not too many people know about us because of our relationship directly with the OEMs. We are owned by a larger company, the Elcor Corporation. They have subsidiaries in roofing products. We do have roofing, fiberglass roofing plants in the south and on the west coast. That seems to be the biggest subsidiary. We have an industrial products group, which we are a part. We're also into engineering and construction of cryogenic technology and natural gas processing equipment through our ProQuip Corporation division. Chromium Corporation is the largest in its field and has been a leader because of its relationship with the OEMs for a number of years. As I said, we do have a working relationship with Cooper on new parts. That was formally announced in 1985. As a result of our working, or our Cooper's requirements, we are also nuclear certified. So that means that we have a system in place for the tracking and complete meeting all the requirements necessary to do work on nuclear components for nuclear work, basically. But what we want to talk about basically today is chrome itself, how we do it, not so much why it works, but we'll touch briefly on some of the characteristics of chrome, but how it works, why it works, and our particular process for finishing. One thing to keep in mind through this whole thing is that chrome is the hardest metal you've got going in the operation of your engine. And a lot of people kind of fail to remember that and realize that the hardness of that metal has got a great great deal to do with a lot of things, but it's tended to be faulted because of that, where unjustly so. Generally, people say, well, the chrome is wearing out this, the chrome is wearing out that, but it isn't really the chrome is doing. There's some other things that can be related. Air filtration, oil filtration play a very big part in how the chrome will react and how it will hold up in a situation. But some of the things to okay, when we talk about chrome, of course, inherently you're talking about the hardness of the metal. Here we just have a chart which compares, according to Rockwell C hardness, cast iron, heat treated and laser hardened. I didn't get all my stuff together here. Which ranges between 20 and 30 Rockwell. And then you have the heat-treated steel, case hardened and nitrided, with those hardnesses out here in the 50 to 60 range. And then conventional chrome plate and our proprietary chemistry. The hardness of chrome can be controlled by the type of chemistry that you use in the plating bath itself. Since we've been in the business for as many years as we have, we've developed our own chemistry, which has some added benefits to it, basically resulting in a little bit of a harder chrome product itself than the conventional, or what you might call off-the-shelf type of chemistry that anybody can go buy it from Marshall or DuPont or those kind of people. And that's generally the chemistry you'll find in a lot of the shops around the country. Because there's no real chemistry involved with it. You just put it in, that's the way it is. But with ours, there's a great deal of maintenance that's required, and we do employ chemical technicians in all the facilities to keep up with the chemistry. Relating the hardness to specific other types of metals, the hardness ranges on the Newt scale from 400 to 1100 Newt, or 41 to 72 Rockwell C, which you saw on the other chart, dependent upon the chemistry. This is a scale of various metals, starting with lead, working its way on down to chromium, and ranking those metals in degree of hardness against one another. In the center here, you'll see copper, nickel, aluminum, going on down through cobalt and tungsten, and chromium still being quite a bit harder than tungsten is. One of the other good things about chrome is that it is a very good conductor of heat. I didn't ask, can everybody see that okay? Specifically, it will conduct heat 5.6 times greater than cast iron will, 6 times greater than ordinary steel. The molecular bonding of chrome to the cast iron or the metal base, the base metal itself, eliminates voids and barriers to the transfer of heat. They said it is a molecular bond, and you'll hear that later on here as we get through this. Molecules of cast iron combining with molecules of chrome that give you a bond strength in excess of 40 up to 60,000 psi directly with the metals intermingled like that. So you have no interface basically between the two metals. You have a combining of chrome molecules and cast iron molecules in the process. Where with sleeving or that type, other types, spray metallizing, those kinds of things, you do have a direct interface between the two metals that you must deal with particularly when you're talking about heat transfer. It does affect heat transfer. Voids do create barriers to the transfer of heat, and you'll see that a lot, as you probably know, in Sweden work in particular. Additionally, Chrome has good corrosion resistance. It isn't the ultimate for corrosion, because as you'll see as we go through this, there is some micro cracking that takes place that does allow some attack over a period of time, but being as hard of a metal as it is, it does provide, in most cases, adequate corrosion resistance, particularly from periods of shutdown and startup where you have a lot of condensation accumulated and things of that sort. And primarily it's used in high-speed engines because of the poor quality of fuels around the world. So everything that we do that goes into the international marketplace is specifically because of poor fuel. The quality of the fuel is very bad and very corrosive, so it does protect the cast iron cylinders against that. Hard chromium also has a very low coefficient of friction. And you see on this chart a comparison with Babbitt on Babbitt, steel on steel, steel on Babbitt, and steel on chromium, and then chromium on chromium. It takes approximately 60% less force to slide a hard chrome-plated surface over a cast iron surface than it would if you're running cast iron on cast iron or steel on steel or something of that sort. Chrome, being as hard as it is, also has some natural lubricity to it. Some other technical factors which explain why it is such a good product for rebuilding is that it does have a very high melting point. 1900 degrees centigrade for chrome compared to 1540 in cast iron. But more important is the fact that it does have a rate of expansion equal to that, or nearly equal to that of cast iron. And you'll see on the chart here, this is just a chart comparing coefficient of expansions of everything from Pyrex glass down to die-cast zinc. Chromium and cast iron, right here, you'll see are very comparable to one another in the coefficient of expansion. So you have the chrome layer and the cast iron layer, and they're not working against one another as the engine heats up or cools down. I do this only so I don't forget something. Now the plating process itself, I have to close. I will have, this is a paper that's written, I don't know if any of you get over to Morgantown in the spring, the Eastern Compression Roundtable. Okay, 1993, I wrote a paper for their book, the conference, and this is the originals of it, explaining what we're going through here in a little bit more detail. But anyone who wants a copy of this is welcome to it. And if you have any questions through the course of this thing, just raise your hand, jump up, and we'll keep it fairly casual and answer as many questions as we go along as possible. And if I don't have the answers, I certainly will get them for you. So we talked about the attributes of hard chromium. The process of electroplating, which is a process used to apply chrome onto another metal, is exactly as the name implies. It's a process that involves an electric current. It is possible to plate without electric current, and that is called, appropriately, electroless plating. But metals such as nickel, are today used to replace chrome in the automobile industry for an ornamental type thing, door handles and a lot of that kind of stuff. No longer chrome, they are nickel, and that's all done with an electroless plating process. The plating process on the liner itself starts with a very detailed preparation of the bore surface itself. After a period of time, that surface becomes, the metal on that surface becomes smeared, and besides being dirty and all that, but that metal becomes smeared and what we call a smut layer develops on that cast iron surface. So all that must be removed, and a fresh metal surface must be brought up to plate on. You need a fresh metal surface to ensure good adhesion and good bonding between the chrome and the cast iron. The preparation of that metal surface is absolutely paramount to having a good chrome surface to work with. And the care that's taken in that preparation will very definitely be reflected in the final product. So we spend more time preparing the liner to chrome plate it than we do actually finishing the liner once it's chrome plated. Now we talked about adhesion, and I did mention that bond strengths of 40 to 60,000 psi are ordinary. In our process, we prove adhesion periodically through the production process. Unfortunately, it is a destructive test. We actually take a liner out of process. It isn't one that's put in the process specifically for the purpose of testing. It is a regular ordinary production liner. And we cut a coupon out of it, just like this. This is one, as a matter of fact. Drill through the back of the coupon to within a 1/16 of an inch of the chrome surface itself, and then with a hydraulic punch or press, we punch a button out of that surface, or out of that cast. And that button is then checked, as well as the crater that was created by that process. And I'll pass this around, you can look at it very closely. Well, what we look for is the chrome actually adhering to that surface, hanging on to that surface, where as much pressure is exerted to crack that off there and bust that off up there. You look at the formation of the way it cracked from there. And you'll see in that the chrome really, that's a water jacket side there of that particular liner. Yeah. And then we rate them from poor, fair to good to excellent. And you can see the difference here, particularly in this area. The black lines there being the chrome, and it did not adhere to the base metal in that situation. Here it tried to, but it did not completely adhere. And here there's just very little distinction between the chrome layer and the cast iron boundary when it's fractured away. But this test is the only way you can truly test adhesion. And what that does is prove the process itself. In other words, the process has steps A, B, C, and D. And if those steps are performed correctly, then good adhesion is ensured, and we prove it and test it in this manner. So that part of the process is all pretty well set and very well, has to be very well controlled to end up with a chrome product that'll stick. And that, of course, being the most important part of it. Once the pre-plate process has taken place, then we begin plating the liner itself.
Is the pre-plate what we're seeing on this one, or is that the finished plate?
That's actually the finished plate. That is what we call the tank finish. Now that finish, as you'll see, is grainy. And you'll see, and note the little round balls like in it. That is characteristic of hard chrome plating. And there again, that is why the free plate process is important. What do you do with those markers, Jeffrey? I'll back up here a little bit to answer your question. Chrome, say this is the surface of the liner, and in a two-cycle, of course, you have the ports opening up. Besides preparing the surface of the bore itself, I don't know, in the alphas you don't have that problem, but in preparing the bore surface itself, you must also prepare the edges. Wherever there's a sharp edge, chrome will not plate. And as you see on that test coupon, there's like little balls. And that's characteristic of chrome plate. It plates in little balls. So when it gets to a sharp corner, then it tends to plate away from that corner as it's laying down its layers. And you end up with a big corner out there that then breaks off. It'll just come right off of itself at that corner, exposing that corner to more attack, or more wear, higher wear than the rest of the bore. So all of the edges must be broke down in radius so that the chrome will actually plate around it without building up. On the diesel locomotives as well as on the large Cooper two-cycles, it's absolutely critical that that those things, all of the edges are broken. The chrome plating process, did I answer that question? The chrome plating process itself takes place with the part, the area to be chrome plated, submerged in a solution of chromic acid. Now, we have tanks for this process that hold 1,100 to 2,000 gallons of chromic acid solution, and we'll plate 4 stations or 4 liners at a time. Wherever you want the chrome to plate needs to be exposed to the solution. It needs to be in a lined tank to hold the quantity, and it also must be bussed to supply up to 10, 15,000 amps, depending upon the size of the part, at 6 volts. So you need quite a setup in order just to start chrome plating the liner. And additionally, the liner itself, if this with a liner, must be fixtured to what we call a rack, which conducts the electric current. The part itself, the liner in this case, becomes what is known as the cathode. And the liner, inserted down through the center of the liner, is a tube that has very definite spacing. It's big enough to allow at least a ½ inch of spacing down to as much as a ¼ inch of spacing between itself and the liner surface that you're plating.
How critical is that spacing?
Absolutely critical, even in that small an area.
What happens to the chrome plating surface on a liner if one side of the liner is a ½ inch and the other side is only 3/8?
One side I'll put more chrome on than the other one. The distance controls the rate of deposition as well as the amount of chrome that's applied. So it is possible to actually change the center line of the bore if that anode itself is not centered in the part. And you can see, depending upon whether the cylinder is set up in a V configuration where you have a thrust and anti-thrust side to it, you can see the wear develop just exactly that way. The wear isn't developing on the top side. May very well be that chrome display goes in. You should see the word develop more on the bottom side. On the thrust side of the cylinder than you do on the top side. But electroplating is basically using the electricity to provide positive and negative fields that will attract. So with the part itself being the cathode, it conducts electricity charging the molecules of chrome to the positive side and thus bonding to the negative part. The negative part of the negative electrical charge of the part itself. The positive electricity conducted through the anode is sent out through the chemistry, through the chromium solution, charging it and thus activating the negative surface of the part, causing the molecular bonding of the two. Sometimes compared to as a weld, but not really quite that. Not really quite that good. I say good, but it's not correct either. But basically, the principle's almost the same.
How close of tolerance do you allow on that?
Spacing?
On that spacing?
16th of an inch. Top to bottom must be centered within a 16th of an inch, and they use calipers to determine that. And the rack itself on the top has actually 8 to 12 adjusting bolts where they can torque the anode any way they want to do that in order to line it up. That's checked on every part before it goes in the tank.
How much difference, let's say you're a 16th of an inch off. How much difference is the thickness of the chrome from one side to the other? How much difference?
Plating, I can't answer that specifically because there are some other things that have to come into play. How thick was the plate supposed to be to start with? Which means how long is it going to be in the plating tank? You can see on heavier thickness of chrome. Now, we can plate the OEM spec for maximum chrome plate is 120 thousandths. So if you're going to plate 120 thousandths and the rate of plate, because it's all a time process, and I'll get into that a little more, but the rate of plate at 1.5 to 2 thousandths an hour for 120 thousandths, 60 hours of plating, a lot can happen and you're building up an awful lot of material. It would be much more obvious the thicker the plate is required. With a 30 thousandths plate, you probably wouldn't notice 10 thousandths, but that's 30%. So 30% on 120 thousandths is 50 thousandths. So it could change it that much, and most of the particular four cycles will tolerate maybe 5 thousandths of change in the center line of the bore and the piston. That's at least what GE tells us for their particular engine, which is an old Cooper. I don't know how is the piston rod hooked up on a 530? I really don't know. Is it a floating piston or is it got a pin?
It's floating.
It's got a wrist pin. Okay. So that would have a bearing on it. Where? So as I said, the plating process itself is a time process, and the chemistry that's being used will control the amount of time it takes to plate it. We consider our chemistry to be high speed, which on the diesel, on the locomotive liners, the high-speed diesel liners, will plate as fast as 3 thousandths an hour. Now, in a high production situation, that means quite a bit. The difference of 1,000th does mean quite a bit. A conventional chrome plating bath will plate basically 1 to 1.5 thousandths an hour. So, one of the things we must do in the preparation liner is, of course, hone that board to clean up that surface, straighten it up, and line it back up as well. So within 2 thousandths, out around and taper both. and then fine the plate so that you get back to original size and then grind stock on top of that. 30 thousandths plate basically is a new liner. Most of the worn liners will go 60 to 100 thousandths without any problem. So as you can see, you're looking at 15 to 30 hours of plating time. And during that time, there are several factors that must be controlled. Temperature of the bath itself cannot fluctuate more than plus or minus 3 degrees. The amperage itself can't fluctuate more than 100 amps. It must stay constant within a half a volt, basically, 6 volts. The impurities in the plating tank itself can't rise dramatically as well. Impurities, the primary impurities in the plating bath is iron, which is etched off of the part itself to some degree. And in those terms, you're looking at 3 grams per liter of iron being a high level of contamination, enough to affect the quality of the plate itself. High temperature, high iron, high amperage will cause a very rough finished plate. And when you're finishing the liner, when you're relying on the plating process to contribute to the end product, the porosity or the finish or the smoothness of that bore, you need to control all of those factors while the liner is being plated in order to assure that you are able to get the correct finish or the spec finish for that particular liner. So the control of the chemistry is just super important to the end product. This, I think, for information's sake, this is about 30 to 40 thousandths of chrome on this particular coupon. We talked about the cleanliness of the surface and things of that sort. Something as little as laying a hand in that board to move the liner or something like that can cause enough contamination of that surface to affect adhesion. So the care must be taken, and you really mustn't prepare the liner too far in advance of when it's actually going to be wrapped up and plated, because it can affect the bond. Another thing that can happen is any interruption in electric current during the plating cycle actually stops the plating process right there. Even a little glitch, such as we have at home every once in a while, when the storm comes by, the lights will go off and come right back on. That stops the process, even for a multi-second, or a millisecond, or whatever. But then it comes back on, and you've created a boundary between 2 layers of chrome. They'll continue to plate, but you will have absolutely no adhesion at that point, at the point where it went down. So what happens in that, if you don't catch it in the honing process, it'll come off in the honing process. It should come off in the honing process, depending upon where it was in that thickness. If it's a real thick plate and it's real early in the cycle, it may not come off because the rest of the chrome that's built up on there will act like a sleeve and protect it. It'll come off in your engine top. But you actually have an interface there where there's no bond whatsoever. And it'll come off like ice falling off of a window pane. It'll just drop like a sheet. It sounds to me like somebody's seen that.
Yeah, I think we're seeing it in the right now.
Could very well be.
So you're talking about a lot of one time was a pretty big chunk. Pretty big problem. You don't look like peeling your apple.
Some kind of contamination, or it could very well have been an interruption.
I don't think it was an well, I suppose it could have been. I'd be more inclined.
If it was localized, it probably wasn't.
I'm more inclined to think it was grease on the line or something. Touching or something.
Exactly. That's all it takes. It doesn't take much at all.
That contamination that takes place, like you said, a hand on the inside of the liner, how far out away from that fingerprint is that chrome? Should that come off and outside where it?
Generally, it can permeate because you have an oil that's there, and as that part gets heated up, plating temperature is only 130 degrees, but it can, radiate a little bit, but you wouldn't find it all the way around the board. You find it pretty low. Is this coming off on an end or down in the middle?
Middle of the top,
Yeah.
take the chain.
Naturally, that's where somebody's going to grab it. And when they roll it,
As a matter of fact, work 3 inches from the top. Chuck by the big hole up there.
Yeah, yeah. And I've seen that happen as well.
What's the little So those holes in the chrome, is that the balls?
What they call pits or comets,
Yeah, they're-
things like that?
Yeah, just a part of the process.
Yes and no, it doesn't have to be. The chrome, as I mentioned before, the care that's taken in the preparation of the chrome surface is reflected in the chrome because chrome does not flow. When it's plating on, it doesn't flow like paint on the wall or anything like that. It plates in those little nodules like this. And it builds on itself until it reaches a point, and then it builds on more after that. But it doesn't flow and fill holes, casting pits, sand holes, those kinds of things. It plates out in a way that,
Like smooth the insert.
no, not like nickel, not like a softer metal that will fill and cover it over. Chrome, you have a crater caused by a pit. First of all, you may have a sharp edge, which we talked about before. It will actually plate away from that, making that hole twice as big as it was for this one. So depending upon the thickness of the chrome that you have, it can control the size of the pit that you have. Now, this is such a common occurrence because you can't control the cast iron. You can't control the quality of cast iron that well. That the OEMs have a spec that says pits up to 1/4 inch in diameter are permitted outside the ring travel area. Now that's the maximum that's allowable, and that must be out away from there. Now, if you've got control of your process, you shouldn't be plating 1/4 inch pits to start with. I mean, that's something generally somebody would want to even want to pin it, and that's a major hole repair that big. But in fact, when another thing that will cause it, besides the casting pit, will be if in the plating process you're creating hydrogen. This is going in. And the flow of hydrogen is to the surface, and it actually boils and rolls. It's not hot enough to boil, but it's just really cooking. The hydrogen coming off of the process, off the liner from the plating process itself, is quite a violent reaction on the surface of the chromic acid. So if you get something caught or trapped, a piece of grit, a piece of debris of some kind, gets caught on the surface of that liner, the flow of the rapid flow of the solution past that piece of debris creates a tail. So you actually get a hole with a tail on it, and the tail will always be going in the direction of the flow of the hydrogen gases. That will cause a depression or a hole in the plate as well. And depending upon, again, whatever the thickness might be, you may plate right over that, and in time, as it wears, you'll come into that particular hole and open it up from the ringwork on that surface. But they call those comets, and there is an OEM spec on it. Pits themselves are generally from casting defects, and there is a certain number of those of certain sizes that are allowed, and comets as well. But as I said,
Excuse me, go ahead.
sure.
How large an area can that possibly be?
The
When you
comet?
talk about this piece of debris catching somewhere and causing that trail, is that,
I've seen them as much
is that trail actually look like a groove in the chrome then?
But I don't recall ever seeing anything more than an inch long. Ball on the table. I don't recall ever seeing anything much more than an inch long. I have to say, I think that in our plating, we don't see this as an ordinary problem. This would be rare, not common like that. You'll see casting pits because you just can't control those. But that's what the honing process is supposed to do. It's supposed to remove any of those inclusions in that surface get you to a clean all the way around. One of the things that we do to control that, as well as prepare the surfaces, we come back and we fine grit blast that bore surface before it's plated. And then our startup process goes through it's a reverse plate is what it is, which causes a scrubbing action to take place on that surface of hydrogen gas. It scrubs itself clean of any debris left from the blasting process. And then they do take with a solvent and wipe out the board for cleaning to get degrees. But what we see is more of the pitting. And not so much of the counts. I lost my train of thought. The pitting spec, I think, is like 10 or 12 pits, so 1/16 of an inch in any 1 square inch is acceptable. Something of that sort. And I'm talking about the spec of Cooper spec. But
That's a lot of pits.
it really is. But it'd be out of the ordinary for us to see that. Because we spent, I know, I was getting back to, when we blast, one of the reasons we blast this, or when we do blast that surface with fine grit, it tends to draw out of the pits moisture in solution from the honing process or something like that that's in those holes, and we'll be able to identify those pits. They'll show up as a dot, and then the solution has, through capillary reactions, shows up right in that, on that surface. So we can go back and correct that right away. But those are that's one of the major problems is the surface that you're trying to plate on. It's got to be prepared correctly, adequately enough. Plating, of course, after it's chrome plated, it has to be finished. And the chrome plate itself has a natural porosity to it. Porosity in the form of cracks in the chrome. And we'll be talking about this more as we get into the finishing of the liners. But chrome being as brittle and as hard as it is, it does stress relieve itself through the plating process. So as you start out the process, the chrome layer will reach a point and then it'll fracture. They call this micro cracking. It isn't readily visible with the naked eye. You do have to use instruments to be able to see it at that point. But as the layer continues to develop, as it continues to build the thickness, again, on top of that first point where it's stress relieved, builds another layer and then stress relieves that. So you get multiple layers of stress relieved chrome throughout the total thickness of the board, of the coating. And again, as I say, you can't see these until the liner's been stress relieved again, maybe in the operation of the engine. And then what you end up is what I'm sure most of you have seen, and that's a chicken wire pattern on the chrome surface. That's really the better picture of the two here. But what has happened there is that liner has been subjected to heat through a failure in the cooling system or something, and it stress relieved the chrome, and that pattern then reveals itself much more obviously on the surface. The chrome actually cracks.
That chrome is coming off the...
No.
It's not?
No. It's a natural occurrence in the thing. All it did was exaggerate.
Even the chrome itself.
No, it doesn't affect adhesion.
Cracks look like they're pretty wide.
Yeah, they do. I agree. I know what you're thinking because a lot of people, that's the first thing they look like. Well, they wouldn't use that liner. You have to have to.
I would
It's a
use
Cooper
it.
GMB. No. But it does not affect adhesion because adhesion takes place in the first 4 seconds.
Okay, what does it do to open something?
Well, of course, you've got more channels that are going to hold oil and those kinds of things. I mean, there's other reasons for changing the liner other, yeah. I mean, you're going to get higher ring wear with that kind of a thing. Yeah, I don't disagree that it would
Chrome would
probably
be not any more subject to off at that point.
No, not any more than it was when you started it up. The bond has already taken place, and it is a molecular bond. You don't have anything to interfere with that part of it at that point. The first few seconds of the plating process, bonding is established, unless there's a contamination somewhere on that board. But from that point on, the chrome is stress relieving, and all the high heat condition did was exaggerate and stress relieve that chrome a little bit more. It didn't affect the adhesion, it just affected the tension of the chrome itself.
Are you controlling this part of the process, control your porosity then too?
It's contributed to the final porosity, yes. More so with other people's than it is with our process, but yes.
More porous chrome means that there's actually more of those cracks in the chrome.
I'll get into what's called the reverse current etch process, where they actually, this is a cross-section. This is a cross-section of that microcracking phenomenon. And you can see rather distinctly that there is some layering that takes place as those cracks take place, but you don't see any of these up in the thickness radiating down into the base metal. You only see that in the first tenths of a thousandth of chrome. But you see, from the side view, you see this kind of stress relieving as that chrome builds up. From the top, it looks like this through a microscope, looking down on it. That's totally natural and present in every kind of chrome, including decorative chrome. That's why you see, like on the old bumpers, some of you guys remember chrome bumpers. In time, you'll see that pattern develop as the water gets behind it, and that's what happens to it. But what our process does is it uses some of that porosity. As you hone this surface away, of course you open up some of these little inclusions. And as it wears away, you work down into more of that stress cracking. Again, you can't see it, but it is there. And it does contribute to the overall porosity of that finish. Reverse current etching is one method of using this characteristic in chrome to establish actually all the porosity they're going to put into the liner, and it's most common use. We don't use reverse current etching. We use what's called mechanically induced porosity. We use this, but not to the degree that most of the other platers in this business do. It's an easy process. You put the liner back in the plating tank, reverse the flow of current, and you dissolve the chrome off of that surface. It starts at the line of least resistance, these cracks, and it starts widening and dissolving away these cracks to widen them and make them deeper and deepen. And that's the whole basis for the porosity. Some slight changes in porosity will get you away from that chicken wire pattern into a more what they call pinpoint pattern, but that's a method that's used by most of the players in this business to get the porosity. All of the control factors, temperature, amperage, and so on, they all play a part in the deplating process equally as it did in the plating process itself. So they are all important just to dissolve the chrome off that surface to establish a basis for porosity. The main thing, the biggest concern is that you can apply a finish to that hard chrome that will operate under the conditions of a particular type of engine, the circumstances or the location, particular environment, and things of that sort. we do what is called mechanically, we use a method called mechanically induced porosity, where in addition to the microcracking, we impinge the chrome surface with grains, hard grits, through a blasting process that's controlled for pressure, speed, feed, and so on and so forth. We also use diamond honing tools, and they in turn impart the proper crosshatch angle, as well as a degree of surface porosity, and not necessarily the surface, but porosity to that chrome. Crosshatch and control of the number and the size of the pores on that surface are what gives you the life of that chrome, you might say. Cooper has very specific requirements for the amount of porosity in any liner. Two-cycle liners, for example, has 3 different zones of porosity, the amounts of porosity that they want in their liners. You can't control the reverse current edge method to that extent. It's either the whole bore or nothing, or you get involved in masking off areas and plating one part of it for a specific period of time and another part of it a little longer, and so on and so forth, in order to work out the zoning. One of the other things that's important when we talk about porosity control, with reverse current edge, put this one understand. This is a cross section. The cast iron base metal on here, and then the chrome layer in there, and the reverse etched surface of the chrome. One of the things that we try to do and must do to provide a good running surface is to give you as close a relationship between the percentage of porosity, the number of pores in that chrome surface, and flat ring-bearing surface. In other words, ideally, if we have, say, 30% porosity, in other words, 30% of any 1 square inch has a hole in it that will retain lube, you should have as close to a 70% flat surface to carry the rings, to support the rings as they travel through the bore. That's the ideal situation. As close as you can get to that, the better you are. With reverse current etching, you'll note that there's a lot of rounding, and if you can imagine how an alka seltzer dissolves in water, it gets very ragged and rough. So when you talk about ring-bearing surface, there is less of a relationship between the porosity, the real porosity, and the ring-bearing surface that you would have if you're actually applying that porosity through some mechanical method, because you can control the depth, the size of the hole, and the sharpness of that hole itself. And that those are your oil retention pockets, in addition to the microcracking that comes out of that chrome surface too. So what you're striving to do is get as close to a relationship between the ring-bearing surface and the porosity, and you do that through a method of through a combination of honing and blasting, or whatever it takes to do that. Now, this is a comparison, this is an example of a comparison between reverse current edge porosity and the mechanically induced porosity. Basically, the two processes are the same as far as preparation and plating are concerned, and after plate. And then there is the finish home process step involved. With reverse current etching, it goes back into the plating tank, and the microcracking is exposed through the etching process itself, and you end up with rounded features on the surface, not quite as well controlled as mechanically induced. With mechanically induced porosity, you may go back into the blaster. The honing process itself will impart porosity in the form of a crosshatch, and the honing process itself will reveal more pores. But when you put them both back through a final honing process that corrects that surface and eliminates any burrs from the blasting, but in the reverse current etch, it's trying to establish that flat ring carrying surface. So they hone it, but you still end up with the rounded pockets and not quite as much ring bearing surface as you do with mechanically etched. In the diesel locomotive liners, we come back and put what's called a final mat to it, which is a 240 grit aluminum oxide blast on the surface that roughs it up slightly, but it's mainly used to seat the rings, hones the rings in pretty quick. And then it's gone. That surface is gone, and you're working on the other porosity that you put into it.
What was the grit?
240 at high speed in a blaster.
What, are you using any liquid in it, or just dry blast?
I just try mine.
Do you have any idea what the porosity ratios are in oil liners?
No, I really don't. I think you probably, we could find out. We could find out, and I'll show you how to do that. In fact, you can find out yourself. I'll teach you how to do that. But probably, I'd say 30 to 40% would be, you could probably expect that.
Why is
Four
it-
cycle, huh?
Go ahead.
That's right.
No.
4 cycles run wetter than a 2 cycle. So you don't need quite as much porosity. They naturally run wetter. The EMD liner, for example, and I'll show you one of our finishes that we developed for the General Motors locomotive with a whole lot of controlled porosity and zone porosity as well. But we came up with this pattern because we dried up the 2 cycle. We didn't put as much porosity into that chrome surface, so it won't retain as much. And you're talking, the difference between a 2 cycle and a 4 cycle can be as much as 90%. 2 cycle will run nearly 100% wetter, or 4 cycle will run that much wetter than or drier, I'm sorry. 2 cycle will run 90% wetter than a 4 cycle. And so we took advantage of that. We dried up the locomotive, so we dried up the cylinder. So the railroads aren't using as much lube, and they're not blowing it out of stack.
Why is there's no cross action on a liner?
Should be. Could be their ground. Could be their ground instead of being home. But there very definitely should be, and I'll show you there. I have got a cause and effect chart to show you here as we get into this more.
You can see it with the eye.
Oh, absolutely. Absolutely. There should be a cross hatch, and there's a very good reason for that. That, one, as well as retaining porosity, or retaining lube, gives you, again, keeps those rings clean.
What if we told you we were retaining too much lube?
We can dry it up.
What if we
If
told
that's,
you
if that's the cause of it.
What if we told you there was no crosshatch, but we're using a lot of lube?
Well, you're getting it by the rings now.
Tell me something, this 240 blast that you do, is that machine controlled? Operated by a human?
Preset. He just starts it, loads it and starts it. In fact, the one that we had in Cleveland in our electric plant doesn't have it yet. They went to an air machine, but ours, the ones we had in Cleveland were Slinger. And the feed of the grip to the head was controlled and everything.
The reason I asked amongst the other question about why we don't see crosshatch, we have found liners that have areas in them which when you go into a liner with an inside mic and you start reading bore dimensions, we've been able to isolate areas sometimes as big around as this and fairly well controlled as far as the OB being pretty round. But you can walk a dial in, or not a dial in through, but an inside mic through that area and find those low spots in our liner. Some of them as much
Does
as
it look like a
3,000.
barber pole?
No,
Just in an isolated spot, okay.
but sometimes 3,000 feet. Why?
A couple things could cause that. Going back to what I said initially about prep, they didn't check the cast iron bore after they honed it, if they in fact honed it for plating. You'll see this sometimes when if they're grinding it rather than honing it. You'll get some isolated spots, but they'll heat up and the liner will expand. The liner could get hot. They didn't keep it cooled down while they were honing it. A lot of pressure exerted in the grinding or the honing process, and there's a lot of heat generated. It could just be expansion at that particular point. For whatever reason, didn't get enough coolant, or the tool got hot. But there has to be a depression, a low spot in the base metal, for there to be a low spot in the chrome.
Well, if they're truing those liners up and making the bores true, then
But how are they doing it?
it makes no difference to me how they're doing it. Why do I have what I got when I get it?
They didn't check it. They didn't find it.
You know, in a honing process or a grinding process, if that depression was there before they started grinding or honing, why didn't they see it while they were honing or grinding? It should show up in a different color if nothing else.
Absolutely. Exactly. And I don't have an answer for it. Somebody didn't see it. Somebody just didn't catch it. But it's not a part that doesn't happen in the process. There's nothing in the process that's hot enough.
No,
But I'm saying, yeah.
I'm just throwing out
Yeah.
things that I'm finding that really puzzle me.
I have to say, not only there was somebody dropped the ball in a final inspection, but somebody up the line before it was even plated should have been able to identify the problem. So you have to look at where are their inspection points. Do they actually inspect the liner after it's been ground, honed, plate before plating? Chances are they probably don't. So whatever comes out of that plate is what happened before it got plated.
How would a liner get out of the warehouse how do I want to say it?
What's the low spot?
If a liner, no, but I mean, I got another instance. How would a liner get away from there that is not around?
When you check for out around, you should be using the dowel bore gauge, number one. If they're not using the dowel bore gauge and they're using a pin mic or something of that sort, it's really tough. You can get more finite with the dowel bore gauge and going down through that bore, and you can see where the height, you can see where the size changes much more readily and much easier. If you're going down through the bore with the dowel bore gauge, then you go 90 degrees and you see 2,000 difference between the two readings going down through the bore. Cast steel liners, or spun cast steel liners, sometimes will reflect the barber pole problem, where they actually, the liner stress relieved and try to unscrew itself, basically, from the spiral casting. And you'll see that kind of a phenomenon in that kind of a casting. But basically, being cast iron, it was just something that somebody missed. Might have been because there was just a localized spot of high wear from the operation of the engine before. But
10,000s out around on the ID and the OD.
those liners aren't very thick. You can drop them, not kick it over, and throw it out around that much. I'll show you how to put it back. You drop on the other side.
We've caused liners to go back around.
Sure.
It's just, that's just kind of odd if we had one show up with 10,000 out around.
Could have happened in shipping,
Well, that's right.
could have happened, but a lot of times you can see that and it'll be on the end, as opposed to down in the middle of the liner. The closer you get to that flange, the stiffer of course it's going to get, the stuff will be.
The one that was out around up there at Sioux Falls, that was end to end.
Was it?
The whole end.
Yeah.
Yeah, just like somebody sat on.
Yeah.
Big son of a gun.
Somebody missed it. Either they weren't checking for it or
Well,
they dropped it from a 7-story window or something.
There. I was curious.
Yeah. What in the mechanically induced porosity process, we do what's called a semi-plateau honing. It gets back to correcting the surface to develop a closer relationship between the pores and the flat surface. So, although it's not a true plateau home finish, it's what we kind of refer to as a semi-plateau home finish because we are actually coming back and correcting that surface to get a more direct relationship with the amount of porosity that's there. Mechanically induced porosity. This is, you saw in that picture, this is an example of reverse current edge porosity. Mechanically induced porosity under the same magnification looks more like a moonscape. There are very definite pockets to it as opposed to the chicken wire or alligator pattern or what have you. It acts more like a blotter than channeling the lubrication through the chicken wire pattern.
Glass beads, you said with 240 grit, did you find a break-in?
We don't do that on the large line, on the big liners, but on the high-speed diesels we do. Yes.
Or you don't do it on like ours?
No, on the big ones. I don't think they're doing it on the alpha factory units. Are they? They coming to you looking real gray, or are they?
Yeah, great.
Okay, then they've matted them. I'm sorry.
Do you get some initial wear on your rings with that surface?
That's the intent. Is to actually hone those.
It's actually initially destruction to the ring.
No, it seats the rings. It seats the rings to that particular bore.
But I mean, you get some wear on the rings.
Just surface wear, yes. It only takes.
It smooths that liner out as that wears off.
Well, that's where we get into the base porosity that's in there, and the depth of the porosity. But more often than not, it's debris in the oil or debris in the air that will create wear and give you kind of a polishing effect to that chrome. You're not going to wear this again. We get back to what I said initially. Chrome is the hardest thing you got going in there. You can polish the hell out of it. But it takes quite a bit of debris in there. Something has to be in there to work on that surface long enough to begin wearing it down. You get the ring wear at the ends because the ring is actually flopping and digging in. It keeps chunking into the end of the liner. And you'll get that kind of a wear on the ends because of that kind of thing. But through the stroke, it's relatively smooth, easy, even, constant. And if you've got something working back and forth in there, then it just starts polishing. And generally caused by debris of some sort. And once the debris starts, then it just generates more. So other than flushing the system or changing the air filters or something of that sort, it's going to continue to generate.
So we receive the liners, we should clean them and all
Oh,
those
yeah.
things.
And you should clean them, very definitely. And the best way to clean them is just hot soapy water and a 10 pico brush. The hotter and soapier the better. Because what happens, and what you might be seeing in your grind, in those liners that you can't find a crosshatch in, is you might see grinding debris packed into the porosity of that chrome that's finally coming out, or it comes out in the operation. That's why grinding isn't really recommended for chrome. But a lot of people do it because it's the only way they can do it. Grinders are a lot cheaper
Was
than
an alpha OEM liner ground then?
an Alpha OEM, the 251 or 539?
539.
Anyone that, we did them, and we always own them. Up until, and I'd say the last Alco 539 that I can recall was probably around 1986 or 1987, something like that we did. Now, if they went someplace else, I have no idea. But Alco and Baldwin was about the same time. Baldwin kind of died off about the same time.
This 240 grit blast that you put on there, do you recommend then that on every overhaul that we change our liners out?
No, we recommend that you clean them.
Wash them
Scrub them clean, and that'll expose some of that porosity that's been packed in.
But just because you change rings and pistons, you don't have to change liners?
Well, ideally, yeah. If you had a way of putting that kind of a finish back on that surface that would help seat those rings, fine. It'll just take a little longer for those rings to seat when you start them up again. But getting in there with a hand hone isn't going to do hardly anything for you.
Well, you're done with this home.
I would venture to say you can use this method. I'll show you how to do this. Take a fax phone. And you can check it before you hone it and check it after you hone it. Just see how much you do to it, damage you do to it. Again, you're using it as in a slurry, wet.
Yeah.
It takes an awful lot of force in a hone to get those stones out on that chrome surface to remove any of it. Now we try to target 12 thousandths over zero in grind stock or honing stock to hone it back to zero. And that's quite a bit to remove. It takes a little bit of doing, even with a mechanical hone with hydraulic expansion on those tools. So, you know, a guy in there with a hand hone isn't going to do much more than polish the darn thing. And again, if you don't clean that bore after you've done that, particularly with a slurry, you've got that stuff packed into the porosity. It's good to get in there and scrub it out.
Is there a reason why you guys would possibly be trying to wash most of that out before it leaves your place?
We do. We do. In our process, it includes actually it's a reverse plate reverse operation in a caustic bath where we shoot electric current through it. And it actually creates some hydrogen which scrubs that surface and will clean out pores, remove rust and everything else, all of the debris from the process is removed in that particular process.
That's showing up on all those crossings, those samples there?
Exactly. It'll be there. These here are four. I've got a matte finish over the top of them. If you look close, you can see it. We'll take some fax ones and you may be able to see it in there too.
What kind of finish is that?
Well,
It's a matte type finish?
well, that gray. We call it a matte. Basically, it's a real fine grit aluminum oxide glass.
Okay.
It's a real fine finish on that edge that will hone the rings. This has got a matte finish, but it's in a barber pole like. That's the one there. You just see the barber pole that actually goes away as the rings seat. In a marine application, when we first ran this, that finish actually seated the rings in less than 2 hours in an EMD locomotive in a marine application.
And that's from the casting material caused that?
I'm sorry?
That was from the casting material kind of unwinding there, is that what you said?
No. This is actually blasted into that surface.
That finish is?
Yeah.
That's to seat your rings.
That hones the rings in to the bore, and then it's gone. And it just wipes out after first.
But the bright spots in the dough.
Okay, yeah, you see the difference in between the barber pole and the bottom and the top. This is the head end, the top, and the working end. There's different porosity up here than there is in the bottom. And there's a different range of porosity in the middle. We call that zoning of porosity. And there are requirements For example, Cooper has specific requirements in a two-cycle. It's more important in a two-cycle than it is in a four-cycle. But it's possible with the method that we use, mechanically inducing porosity, to control it very finite. 30 to 40% up in the head,
I saw that.
10 to 30% through the port zone, and then down in the skirt end, 5 to 20% is totally within control. And you can see in this particular faxicone here, you can see the crosshatch is more evident in that one. But they all have a crosshatch, and we'll get to a cause and effect paper here before we're done. But basically what that's saying is that in any 1 square inch of this cylinder, 30 to 40% of it has oil retaining pockets.
Is it possible to check that hardness on a porous surface like that?
Now, actually, the best way to check hardness is they take and shape a cross-section off of it and they indent and polish it. They actually polish that surface and eliminate most of that before they check the hardness when they do it in the lab.
What kind of porosity should you expect to see, or not porosity, hardness should we expect to see
In chrome? And I'm sorry, what finish?
in your finish?
In our finish, you should see porosity ranging around 70, Ron, let's see. 70 to 72. Conventional chrome plating baths will range 60 to 65 would be maximum. We're about 10-15% harder than a standard conventional chrome plating chemistry.
How hard should the ring be that runs against this?
We advocate just basic ductile iron rings. Ductile iron rings. Certainly don't want to run a stainless steel ring around on it, but it isn't necessary. The investment isn't necessary. Ductile iron rings will run fine as long as you have the porosity and the finish correct for the engine or for the operation. This is a little history on surface finishing and its effect on oil consumption. This was done by international harvesters. It's just a kind of a history on RMS finish. RMS is root mean square. Another term is RA, which is the arithmetic average of several readings taken on a surface. It's a measure of smoothness of a given surface. To put that in perspective, a sheet of window glass, an ordinary pane of window glass, is about a 7 RA. In the 1970s, Caterpillar and Cummins began changing or reducing the RMS finish on their cylinder bores. Now this is on-road diesel engines, over-the-highway diesel engines, from a range of 45 to 63 RMS to 20 to 40. In other words, they cut it about in half. And the result was that they did see a reduction in oil consumption from 0.75% of fuel consumed in 150,000 miles to extending it to 0.3% of fuel consumed and 200,000 miles. So they were able to extend the life of the engine while reducing the fuel that was consumed, or the oil that was consumed rather, in the life of the engine. In the 80s, they further reduced it down to 10 to 20 RMS. That's pretty smooth. And again, they had a comparable reduction and a doubling of the life of the engine. In 1994, the federal government got involved in mandating some emission standards, which can a good finish, a controlled finish of porosity in a cylinder bore can contribute to some of the reduction in engine emissions as well. The next two items there, the rail industry, the EMD engine consumes 0.90% of oil to fuel, and the GE three-ring consumes 0.10, so there's a dramatic difference between how wet and how dry the two-cycle EMD is compared to the GE. And our finishes over the years have evolved accordingly. The honeycomb pattern, which some of you are familiar with, is in that case. It's the dotted has a dimple pattern that's actually etched into that finish. It's 45 thousandths in diameter and 2 thousandths, 2 to 2.5 thousandths deep. Well, they retain an awful lot of oil in this.
On that order, it says three-ring piston ring consumed. Is that 0.10 of 1% or 10% of oil fuel?
0.10. That is 0.10 of 1.
Of 1%?
Okay. Our open grain matte finish, which has about a 70 to 80 RA, has run over the years 400,000 to 500,000 miles between overhauls and locomotive applications. And we, by coming up with pattern A, reducing the RMS, we've been able to extend the life of locomotives. And likewise, with the whole theory behind the Supor finish, with a further reduced or smoother surface finish and control of porosity, we have locomotives right now at running 1.5 million miles on the same set of liners.
Okay.
And you guys deal in hours, but that's it's a long time. 1.5 million miles in certain applications is 4 years. That's pretty quick, 5, 6 years in some other, in a short line railroad, then you're looking at 15 to 20 years.
So this super finish here is a 30 to 40 RMS,
Right.
and our specs call for a 20 to 30 RMS.
No, you're talking 20 to 30, is that what your spec is?
Yes.
That's really smooth.
That's our spec.
Okay. Yeah, that's relatively smooth. It doesn't deal with percentage of porosity that you want within there, so.
So what should the finish on our liners be like?
Better than this.
So why do we have something worse than what's in that box?
I can't answer that one.
I'll just throw it out.
Yeah.
Because there's nothing in that box that looks like our finish.
Really?
No.
How about that rubber chrome right out?
Right up in the tank?
There's nothing, honeycombs like
Ours looks more like a plastic type etched finish, so it looks more.
Yeah, like I say, that's the easiest way to put porosity into something, and I'll show you some fact zones here that are taken at different times or at after operation. Let me do this here first. This is it? I think this is in that paper. This is a paper that was done by Sealed Power. Typical study of typical bore finishes and their effects on engine performance by Sealed Power out of Muskegon, Michigan.
You think
They are
that page is in
manufacturers
that
of
paper?
rings. Pardon me?
Is that page in that paper that you wrote?
No, it isn't, but you can copy it if you like. I thought it was, but it isn't included. This is a cause and effect type of thing, dealing primarily with crosshatch and plateaued finish. Keep in mind that plateaued finish is a corrected finish that provides you with ring bearing surface. So, number one, wide, deep crosshatch grooves will cause abnormal wear, excessive oil consumption, lengthens break-in period, and it will cause a variation from engine to engine in the performance. Major cause, stonework, too coarse. 4 stone breakdown, coolant viscosity too high, excessive stone pressure. Number 2, crosshatch grooves irregularly spaced, in other words, not uniform in distance, will give you poor oil distribution and variation in braking. And what causes that? Basically, again, it gets back to the process of finishing or honing that surface. Crosshatch grooves folded or fragmented, slows ring seating, causes scratching and high wear, lower life and oil economy, raises ring temperatures, causes excessive variation from engine to engine. Plateau burnish, in other words, it's like a hot spot on the ring travel area. Causes slow seating. In other words, what they've done there is that they hit that too hard with a stone or with their finishing tool and turned it a little blue. Slow seating lowers economy, reduces uniformity engine to engine. And what caused that? Again, it's in the finishing process itself. Choosing the right stones, the right amount of pressure on those stones in the process, and even the right type of coolant. Too little plateau. That means that we're talking about the ratio between porosity and ring-bearing surface. Causes excessive ring temperatures, high wear, shorter life, bore and ring scratching or scuffing. One directional crosshatch. Instead of, it's not really a crosshatch, it's just everything's going one direction. Again, it causes the ring to rotate and increases the wear on the rings, or to almost no ring seating actually, and reduced economy. And again, it gets back to the honing process itself. Low crosshatch angle, the angle's too flat. Poor oil distribution, high impact forces on rings, slower break-in, excessive wear, and short life. Particles embedded in the surface, same effect up here. Slows the ring seating, so on. You'll find that more in when you're grinding them, and they're ground instead of honed. So if you're seeing the things that appear up here in number 3, that may be why. Metal pulled from the bore surface. Basically, that could be done in grinding as well. Most of your spun castings, you'll see some of that more than you will with cast iron. But the whole thing points out to the control that the plater has over the machining part of the process. Plating is plating. There are different ways of getting to the same point. But after you've plated the liner, then you've got to finish it so that it's functional and will give the customer good service at a minimal cost in operations. So, yeah, probably a lot of people can plate these liners, but not everybody can finish them. Honing is the preferred way to finish these, not grinding. Not grinding at all. We used to do it in our Buffalo plant, so we saw how many homes that we've got standing down there, all large vertical homes. Any questions up to this point here?
Chromium doesn't have a recommended rating around the liners.
No. We don't feel that anything much more than a ductile iron ring is economically necessary. Okay, what I want to do now is show you some fact stones. How many people are familiar with what fact stones might be? Okay. Fax film is like taking a fingerprint. Gives you a ability to actually measure the amount of porosity that you have on a surface. So it's turning. And I'll show you how to take them. And I would recommend that you use this method. And one of the things it's really good for, I can't use the carousel because these just won't work in there. Now this is some of you will recognize is actually fax film with honeycomb pattern itself. It's one of the bars that's in that sample case. To say it's like a fingerprint. So what we do is with acetate tape, and I'll leave this with you if you want to use it. With acetate tape and acetone, $2 a can at your auto paint store, you can actually imprint the surface of the board. We'll do that with some of these samples. With the acetone, and pressing a piece of this tape on there, you can actually lift an impression of that surface to the point that you can mount it and project it. Knowing your magnification and the distance you are from the screen, you can figure out, and you can actually grid it and get real technical about it if you want to. But after a while, you learn by looking at it to tell what porosity within a reasonable margin that you actually have. Honeycomb pattern is a bit of an exception. What I'd like to show you now is what we had talked about. This is an example of reverse current edge porosity after a period of 24,000 to 30,000 hours in a marine application. I was in our Cleveland plant one day, and these liners came in, Fairbanks, these were Fairbanks liners, from our customer. And in those liners, they had both reverse current edge porosity and our mechanically induced porosity. Both running the same period of time, in the same engine. So it was a good chance to get a good sample of what the finish looks like after a period of service. This was reverse current edge. Oops. This was mechanically induced porosity after the same service. Still have a moonscape blotter type effect that will retain and hold lube. When we make liners for our OEM customer, we will use fax films periodically to check the finish. And that's what they look like going out to the door on a brand new FM liner. So you can see that after a period of wear, that finish, oh, wrong one. That finish hasn't changed a whole lot from brand new. And under the best of conditions, that's what you should see after a period of service with that particular finish. I talked about zoning of porosity. This is a good example of zone porosity. This is in a Cooper engine. We got an inquiry from Colorado Interstate a few years back to develop a finish for their two-cycle Cooper GMV engines. They wanted a little more porosity in them. They wanted to be able to retain a little more lube oil because they were having some ring wear problems and things like that. So you can actually see the boundaries where the two types of degrees of porosity, percentages of porosity were created in that particular liner. And those are some of the things that you can do with this process. We actually, on new liners, all of the new liners that we do, particularly for Cooper, we're required to take and submit fax films with each liner. So we use microfiche projectors primarily to use as a comparison. We have a standard, an accepted standard on one side, and with every liner that goes to Cooper, we must submit 3 fax films from 3 different areas in that board, and we use this to compare them to standard to ensure that we're inspected in that regard. So the process will produce a finish that can be controlled, and the system that we have to checking that means that every liner gets checked, and so we know that the finish is exactly the spec. Now, to take fax films, I'll show you exactly how to do it. You want to one of those. Where do they go? Which one would you like to see?
Any of them be fine with me.
You want to see
That one
cross
up there would be fine.
I don't know if I see too much in there, that cross hatch. Okay. This is the skirt end, or the bottom end of the liner. So there isn't going to be a whole lot of cross here. We'll just use a cast iron with cross hatch. You'll be able to see that. I've done the soup board before because then I know it's just going to show up. You're going to see a dot here and a dot there. Acetone in a spray bottle, and napkins, and a clean rag. Use the acetone to clean the surface. First off, and it evaporates pretty quick. And then taking a clean piece of acetate, and flowing the solution over that surface. Just keep flooding it. Piece here. Might have gotten a fingerprint in there. And then just let it stand and dry. When you're working on a large liner, you can get both hands involved, and you can just lightly rub it while you're flushing it with the solution, and otherwise it'll get real sticky and you'll get your finger on it. I have instructions on how to do this in writing, and I'll leave those with anybody. But what I recommend you do is, when you first get a cylinder back from being reconditioned, take some fax films off. And the head end, below the ring reversal area, and down in the skirt end. I don't know if you serialize or keep track of your liners that way at all, but you might want to put a number on the liner, put a corresponding number on the tape. Next time there's a question raised in an overall, well, do I take the liners out? Do it again, and then put the 2 up, project them, and look at them. You know exactly what your porosity looks like at that point in time. You can see how much wear. From day 1 to that point, you can see how much wear you actually have in that liner. I recommend this on new liners as well as rebuilt. And then, after a few minutes, you just peel it off. And mount it. These mounts have got room for identification on them. And you can actually see it. Okay? A lot of times what you can't see with the naked eye on there, you can certainly pick up with this tape like that. I probably got that turned sideways. Looks like a pretty steep angle on the crossheads to me.
Oh, there's some rings won't circle so fast.
But it's not hard to do, and I highly recommend it. Not enough people do it as far as I know. After 20,000 hours of service, you do it again, and you throw the two up here and look at them. You know just exactly whether you need to put that, you can put that back in there again or not. If it's got some porosity, if it's got porosity into it, and you can, and it hasn't changed a whole lot from the new one, and your ring reversal area isn't too badly dug up, you may be able to use it, put it back in the same hole. Or you may decide that the ring reversal area is too bad and you need to redo the whole thing.
What happens if you stick them in a different hole?
Well, not all the strokes are the same. And if you're lucky, the stroke might be a little shorter than the other one. The line
Well, when
was
you change your pistons anyway, it doesn't make any difference because your rings aren't going to necessarily be in the same spot.
Well, yeah, but the top of the stroke might vary a little bit, and you might ram a ring through that step and the ring reversal at the top.
And that's what I say, if you change your pistons, that's not going to be the same necessarily anyway.
Well, but yeah, right. But if you have any idea that you may reuse those piston cylinders, I would recommend that you mark them where they came from, or at least with the piston that they came out
We
of.
never use the same pistons over.
Okay.
When we go through an overhaul, you know, I've used the liners 3 and 4 times.
Right.
If there's no step in it, if you can't feel a step in it, but we always replace our pistons.
Replace them with new.
We replace them with a re-groove. Usually.
Are those tin bladed? No, they're aluminum pistons.
See, we don't have enough parts at all locations to maintain spares, so we have some at the warehouse.
Oh, okay. So they don't.
So then they call for an overhaul, they'll call for 6 pistons, come out of the warehouse to the location, take the old ones out, send the machine shop for servicing, back in the warehouse, we just rotate it through. We do the same thing with the liners.
Okay. Well, if you're changing, if you're changing one, you should change the other in the basic. You want to? Sure. And I'll leave the acetate with you. Any questions on how that was done? Pretty simple, really.
Check yours in one.
And acetate, is that?
That's acetate tape, yeah.
Where do you get that at?
Probably some graphics supply house would have it.
Yeah.
Blueprint? Possibly, yeah.
Film Star?
But if you look up acetate in McMaster car, they probably sell you a spool at 500 feet long.
I've got 2 spools like that. If you need any, just call me.
They probably got it from McMaster car, you got 500 feet per spool.
Just trying to get rid of
They
it.
stole it out of our plant because they don't need it anymore in Cleveland. But that's just a down and dirty, simple way to do it. And
You're losing your ass when you go out projecting.
It'd be an interesting place to have it.
that's wood fire. That's the heat from the motor. It's Yes, I had a second front of that house.
Oh, we got fire extinguishers, that's how we can put it down.
So, just to kind of summarize, plating, hard chrome plating is kind of hard chrome plating. There are some advantages with our chemistry and the way we do it as far as the plating process is concerned, though. Hard chrome is hard chrome. It's hard. 62 is, the difference between 62 and 70 may not be too great, but over the years, we have maintained our position in the marketplace, particularly on new liners, because of the hardness of our product. And equally, because of our expertise in the finishing process itself. If that surface can't hold glue, it doesn't matter whether it's chrome or whether it's chocolate pudding. If it can't give you a good life, a good service life, you don't want it.
If we requested 6 liners, and you guys didn't want the brush blast finish on it, would you do that?
In the matte finish.
Matte finish, yeah.
We can do it out there, maybe. Why not?
Because we've had, to be honest with you, we're not getting good oil consumption with your liners. We don't know whether to blame the piston rings or your liners or whatever. We just, our oil consumption been considered a new overhaul, not real whipping.
What happens with a liner like an alpha liner, like the 539, unless you have a very definite spec of your own, when you say, well, we want 60% porosity, we want an RA, do they know that you need a 20 to 30 RA? Is that what you're getting back?
Yeah, I'm not sure what, I know when we were down there, we talked about the porosity, and
Okay.
Ken had looked through the Alco records down there and looked and says, here's what you should do,
Yeah.
here's what you want. And that's it. I started looking through some of the correspondence I've gotten, we don't talk about porosity and RMS and those things, but we're really concerned about this oil consumption, because it's
X-Line hones their liners just like you guys do, but they don't brush blast the finish. And right now, their liners are giving us a lot better oil consumption.
And I don't know what they're providing us for porosity. I know they have that liner sheet that I just had out here. That's the Williams standard sheet, and both Chromium and X-Line have this sheet.
Oh, okay.
These are the dimensions that when you farm it out to the machine shop, that's what they go by, the lining surfaces, everybody has this.
A lot of the problem is created by the fact that people regard RMS the same as porosity.
I know there's difference. I don't know what the porosity is, other than when we first set it up, Ken said, here's the alpha spec, here's what you need. And that's what we went
You
with.
can see X-Line's home marks. You can see their home marks on the lines. I have been see, they may be there, but I just,
On our liners, you
Hard to
can't
see.
see any porosity?
I might be able to see it with a magnifying glass.
Well, with the mat on them, you probably
Yeah,
have
that's good.
difficulty seeing. Yeah, yeah, because it'd be the same thing as trying to find it on one of these.
you can't.
In fact, this is probably
I can see the crosshatch on those.
what close to what you're getting here. But you can't. It's difficult to see through that mat. That's a pattern A. That'll have a little less porosity in it than what you're seeing. You should see in your own. But people will confuse RMS and porosity, and they are totally independent of one another.
But see, I don't know what we're getting from you.
Yeah.
And maybe
I
that's
think that's
something
what
we need to
we
look
have to
at.
find out first what you're getting, and then
Right.
take some steps to ensure that you get more consistency, and perhaps you've got more.
We've had a pretty good share of problems with the liners, or more of a concern, and we're not seeing the same kinds of problems with the X-line liners, but yet we're using the same pistons and rings. You know, that's standard across the company. And we're just, I don't know if we're not used to the procedure you guys have, because, we haven't had them. This is the first time we've used your guys' liners in the last 2 years. We just, otherwise, everything we did was X-line. because of some of the other chrome plating thicknesses you guys can offer, that's why we started coming to you guys.
That's what I would recommend, really, is to take a look at what X-Line's giving you.
Then we need to find out what you guys are looking for.
Yeah, and if, and let us take a look, take some facts from us, let us take a look at it and see if we can identify what the differences might be. Chances are what's happening is that they're using reverse current edge, or maybe they're not.
I think they are.
I think, pretty sure that.
Yeah, and what happens with that is you get a whole lot of porosity. And chances are you might be talking 70, 60, 70% porosity. Or maybe not. You know, it's difficult to say without being able to look at the thing.
Right. But if we take,
If you're getting 60, 70% porosity, then you'd be using some lube. You might be getting that from us, as far as that goes. Because our standard,
Their finish, it appears, and we didn't run any specs or stuff across it, but it appears that your porosity is quite a bit greater than next one, just through the naked eye. Because usually the finer the finish, the porosity.
well, you get more to the shiny
Yeah.
side there.
Is that what you're
Yeah,
getting at?
it isn't likely that you'll have 30 to 40 RMS and have 30, 40% and have 70% porosity. There is not a direct relationship in that regard between the two, but it's possible to have, say, 50% porosity and 30%. They're very close, but it's not possible to be.
well, these RMS specs I've got are from Alco, off of that Alco's drawings. It's nothing we came up with, that's from Alco.
I would say probably they're doing what we call our open grain matte finish, and the porosity of the RMS is probably a lot higher, in the range of 70 to 80, probably double what you require. I think possibly some of it is going to be wrong. It's entirely possible.
There's a in your 140 RMS mentioned there one place on that drawing.
That's on the outer finishes.
I wondered if somebody misread that.
That's something.
I don't know how they process the
Yeah.
liners, but our open grain matte finish is up there in that range of 60, 80 RMS.
I need to work that through with you, Jeff? Okay.
Is there a cost difference between those solutions?
Not the finishes we're talking about. There's a cost difference on this finish, about $25.
How much per liner?
No, this is about $25 higher than
This is superior finish, you call it?
Supor.
Supor. Scientifically uniform porosity and oil retention. Shame.
I thought we had.
This does not work well in a 4-cycle engine. You know, it's just too dry for a 4-cycle. We don't need that kind of a finish for 4-cycle.
But Jeff, the finish we've got is smoother than that, but the porosity could be different.
Yeah,
That's what's
right.
contained in the oil.
Exactly.
Okay.
Exactly. You look at a painted window glass, I said, is a 7RA, 7RMS. Throw oil on it, runs off. Blast it, just hit it with a little bit of grain or something that chips it a little bit. You're still going to have pretty close to the same RA, but now you've got some pockets that'll hold up that oil.
When we send a liner in, do you have to take and pull all the chrome back off of it?
It's stripped off electrochemically. It's actually dissolved or put back into solution. It's not quite a reverse. It can be done that way, but you're also reversing the metal off the liner too, because it attacks the whole liner there. But with a caustic bath and reverse plated in an anode, a steel anode, you can take the chrome right off. Then we go back through the whole honing process again and get bright, fresh metal up to plate on.
It's what they've done, Carl, and the specs that they've got from us that we've agreed to. When we send that counterboard liner in, which is what the most of them send to them, then they will strip it, and then they will hone it straight. And then do the whole chroming. They don't just hone that part of it. So you
The whole
end up
body
with
of
a
the
straight
liner
line.
will be at the same diameter as
Right, and then you're back to the finished product. Within two thousandths taper or 2,007.
Don't want to get them dirty yet.
There's some, Brad, why don't you get those floats out of the, boat and see if anybody wants them? Get those mats. Mats. Inside the pontoon boat, those blue and green